clearly associated with or less clearly explain age changes in intelligence. But when you look at perceptual speed as a measure, you get pretty high associations with intelligence, and even in some modeling of changes in intelligence, actually most of the age-related changes in intelligence do seem to be related to speed. So over the last, let's say, 3 or 4 decades, we've kind of gone from changes in speed of response might explain just about everything that's going on in cognitive aging to not so much. Things are kind of independent, and speed explains some things, but there's a lot of stuff left that's not explained. And then we're sort of coming back to, well, it explains at least a lot of stuff. Maybe not quite everything, but lots more things, including some things that in the past we thought were quite independent. So it's still a pretty strong hypothesis, and as you've seen in some of the readings, it also is related to some of the other cognitive resource variables that we've been looking at. So you can certainly argue that it could be that the reason why working memory seems to be smaller in later life is that if you're processing everything more slowly, then by the time you get to the 5th thing on the list, it's been a lot longer for you since the first thing than it is for a younger person, and so the first thing is more likely to be gone. Whereas for a younger person who's processing things more quickly, they could get up to 7 or 8 by the time you've got to 4 or 5. Something like text comprehension and so forth. Attention is a little more complicated to operationalize, but people also argue that maybe part of what's happening is that you're just not, because you're processing things more slowly, you can't switch back, and particularly if you're talking about attention switching, you can't switch back and forth as much. More things are going to interfere with whatever you're trying to focus on, because some of the stuff that you were focusing on a few minutes ago is still with you, and so you get more interference in that few minute line. Attention and aging, like a lot of cognitive stuff, it kind of depends on what the task actually is. But if you're talking about divided attention tasks, which is where you're, at least as nearly as we can tell in a lab setting, you're trying to do 2 things at exactly the same time. There are pretty clearly age effects on all but the very simplest tasks. This is the whole idea that older adults have trouble screening out background information, screening out irrelevant information, handling lots of information. Sometimes even actually there have been studies that suggest that if you try and give older adults a lot of information that's all on the same point as a way of underlining what you want them to know, the fact that you've got a lot of information, even though it's all sort of related, interferes with learning any of it. You're actually so better off keeping it really simple and slowly presented. And probably in these cases, slowly presented both in terms of chronological time and also just in terms of the number of things that you're trying to present in any one longer session. Selective attention, you definitely get age effects when you have to screen out background information. Divided attention is more like you're actually trying to do 2 things at once and have twin channels of attention going. Selective attention, you're only trying for one focus of attention, but other stuff is getting in your way. Young adults are pretty good at screening out background. Sustained attention, in some ways, is kind of a bit analogous in terms of difficulty getting at it to storage as a memory process and the encoding, storage, retrieval thing. It's depends a bit on what you mean. You kind of typically end up looking at the slope of decline of performance. So older adults tend to be doing worse throughout a sustained attention task So if your definition of sustained attention is the drop-off over time in attention. So sustained attention is you're sitting here looking at the screen, you're waiting for a dot to pop up on the screen, you're going to hit a lever, and the longer anybody at any age has to wait for that dot, the more likely it is you're going to miss it when it shows up. That's what it means for sustained attention. But the drop from the first 10 seconds to 2 or 3 minutes later is about the same, although older people are starting from a lower performance level to begin with than younger people are. So your overall attention is worse, but your decline over time is probably roughly similar to So, more good news. This is the Dairy paper, and I've taught this the longitudinal changes in processing speed with the Fozard et al. Paper that they mentioned in the beginning of theirs. Fozard et al. is based on the Baltimore longitudinal study here in the States. I shifted to this one for this class partly because it's newer. I like to stay up to date. Partly because the sample is a lot larger, and conceptually because of their focus on variability of responding as well as the mean level of the response. And then I had some misgivings even when I picked it out back in August, because it does get really complicated really fast. But as I said in the email this past week, really kind of up to figure 1 is about all that we really need to be concerned about for the class. The other thing I would say, this is just something that's kind of intrigued me about psychology and social sciences since I was in graduate school myself, is that the mathematics of studying like sensation and perception and reaction time gets really, really complicated really, really quickly. I actually talk to the people who do this kind of research. And I think those of us who are more on the kind of the social and clinical end of things in our research interests would assume, and I think we must be right about this, that the processes that we're studying must be a whole lot more complicated than simple reaction time measures. But then we pretty much only ever look for really simple linear effects in the data, and we don't do this more complicated curvilinear modeling and more complex math that these people study, like visual thresholds and reaction time data from here on in. Kind of interesting. I think there's probably all kinds of reasons why we do that, including that we just don't like math that much. But I think it's something that should give us pause on some level, that even though we think that what we're looking at is complicated, that we actually do very simple math. So this is simple reaction time mean. This is the choice reaction time mean. So all we're looking at here is, it's kind of regardless of what happens, you press a lever, what happens, and you see you're waiting for this, and then choice is you have to press different levers for different symbols as they come up. It's not about deciding what graduate school you're going to go to, whether you want to get married this year. It's not like complex choices. It's interesting how different even these fairly simple changes in task are. And the intriguing thing about this, if this turns out to be replicated, is that they find almost no change in reaction